All right, so this is the slide we left off of last time. Trying to figure out what the different types of stars in our galaxy. The different spectral types of stars in our galaxy, where they are, and so forth. It gives us more information about our galaxy, about the history of the galaxy, and so forth. This is a more technical thing. We're not actually going to do any equations with this, but there's a thing called the mass function, which is you got to do the census, and then you have to kind of figure out what the mass of each of those stars are, which of course is determined by the star's position on the HR diagram, right? The stuff that we had back in chapter 13. So remember, stars that are higher up on the main sequence on the HR diagram will they're more massive, but they'll go through their life cycle much faster. This tells us a lot about our galaxy, about the different types of stars in our galaxy, and it also gives us a sense of the future of our own galaxy. How old is it? How much time do we think it's going to be around? As I said before, I think I mentioned this, that the vast majority of stars in the Milky Way galaxy are less massive. They're little tiny red dwarfs. That's what they're called. Roughly about half the mass of our sun. So that's the vast majority of stars. And then, of course, there are some excuse me, some more massive stars. Excuse me, up to around 100 times the mass of the sun. But again, these are extremely rare. But the overall average of all the stars in our galaxy is roughly 1 times the mass of the sun. Excuse me, sorry, I just ate lunch, so. All right, sorry, I had to go get a drink, clear my throat. All right, so yes, so on average, the stars, most stars are not the mass of the sun, but the overall average is roughly the mass of the sun. This is an interesting point. In fact, there are people who devote their careers to studying these things, these so-called brown dwarfs. These are what are considered failed stars, and we're finding more and more of these out there in the Milky Way as time goes on. They're playing a much more significant role than than we realized. In fact, we think that there might even be more failed stars than there are actual stars where thermonuclear fusion is taking place. For example, Jupiter would be an example of a failed star, or one of these brown dwarfs. Jupiter actually emits its own heat, but not because of fusion. Okay, so all right. So now what we're going to do is we're going to look at kind of broadly 2 different populations of stars in the Milky Way. The ones that we find in the disk of the galaxy and in the bulge of the galaxy are called population 1 stars. So population 1 stars are relatively young. Okay, so they're maybe a few billion years old. Like, for example, our sun is roughly 4.5 billion years old. One of the things about Pop 1 stars, that's what they're called sometimes, is Pop 1 and Pop 2 stars. So Pop 1 stars have a significant, or around 2% of their mass is made up of elements heavier than helium. Right? Hydrogen. Here. Let's look at the next slide. They'll kind of we'll get into that in just a minute. Population 2 stars we find in the halo in the globular clusters. In fact, that's what the globular clusters are made of, by and large. They're all POP2 stars. In fact, we're going to find, I'm talking about a little bit in the future, but there's entire galaxies that are made up of just population 2 stars. But that's a story for another day. So the thing that's interesting about these is that population 2 stars have very low metal content. Remember, metals are anything heavier than helium. For astronomers, that's, I know the periodic table is not like, for example, chlorine would not be considered, for a chemist is not considered a metal, but for astronomers, everything heavier than helium is considered a metal. So anyhow, these stars have anywhere from about 1/100th to 1/1000th the metal content compared to that of the sun. All right, so this is an oversimplification, as it's saying here, that we do see some some older population 1 stars in the bulge and so forth. All right, so in fact, we think that the when the Milky Way formed, that very quickly population 2 stars formed right after the collapse of the all the gas that eventually formed the Milky Way, and then eventually once these population 2 stars go supernova, then they spread the metals out into the rest of the galaxy, and then new stars are formed, and the next generation of stars will be heavy, more a higher percentage of metals, and then eventually you get down to about 2% metals, and that's what population 1 stars are now. All right. We also see many different what are called clusters or star clusters. There's two general types: open clusters and globular clusters. We've already mentioned the globular clusters, but we're going to look at that in a little bit more detail. Open clusters can generally have dozens to maybe a few hundred stars that are members of an open cluster. We find these generally in the disk of the galaxy. As it says, this is the typical size of a cluster, an open cluster, anywhere from 7 to about 20 light years across. For example, there's a region, you might have heard of this before. It's called the Pleiades, the Seven Sisters. Actually, I always talk about this. I might as well talk about it, even though this is the online version right now. If you look at the front of this, so this is nothing to do with, not directly to do with astronomy. If you look at the front of cars, right, for example, a Lexus has like kind of an L, like Mazda has an M. What else? Like Toyota has a kind of a T. Honda has an H, a funny looking H, like on the front of a car. There's actually a car company that uses the symbol of the Seven Sisters so there's 7 stars on the front of this car. And it's actually Japanese for the Pleiades, which, of course, that car company is Subaru, right? This isn't a car advertisement or anything like that. It's just talking about the fact that the symbol on the front. If next time you look at a Subaru, or if you happen to own one, you look at the front of it, and there's the Seven Sisters. At any rate, so these are called open clusters. These are stars that are very loosely associated with each other gravitationally, right? As opposed to globular clusters. We'll see that. All right. so that's what I just mentioned. These stars are spreading apart, and so the cluster eventually dissipates. We think that our sun was once part of a cluster of stars. There's a nice picture of the Pleiades right there. The famous Seven Sisters. Here's a couple of more open clusters. Just some pictures of it to give you a sense. This cluster would have hundreds of stars. This one, maybe less than 100. All right, so now globular clusters, their size is anywhere from 40 to 60 light years across, or the radius of a globular cluster. So they could be as big as 120 light years, the diameter. We see about anywhere from 150 to 200 globular clusters. Remember, these are spheres that surround the galaxy. They exist in the halo. They contain anywhere from a few 100,000 stars to some of them have as many as several million stars, but no more than like 2 or 3 million stars. All right, there's some nice pictures. This is probably the most famous one that you can see pretty easily. This is in the M13 is in the constellation Hercules. It's between the two. I'd have to show you a picture of Hercules, but it's like if you look at the constellation Hercules, the two stars on the left hand side. On the right hand side, the M13. You need a telescope to be able to see this, but it's very easily seen, even with a good pair of binoculars. You can see M13. So it's between those two right-hand stars of the constellation. There's 4 bright stars, and I'm talking about the 2 that are on the right. So you go right between the 2, and that's where this thing is. You point your telescope in that direction. There's another globular cluster. Remember, these things, these are really old population 2 stars. Very little metal. They generally show a very reddish appearance. So they're comparing the two. There's the open clusters, young, hot, blue stars, and then the much older reddish stars in the globular clusters. All right, we find that there's actually a lot of gas and dust in the Milky Way, and we have to compensate for that. This is, of course, not a picture of the Milky Way. We can't get this kind of a picture. We can't get that far away from the Milky Way. This is a very famous galaxy. There's many galaxies out there. This is sometimes called the Sombrero Galaxy. You can clearly see the gas and dust surrounding the disk. Or really, the gas and dust is there all around, but it's just being highlighted by blocking some of the light in the disk, and that's really what you're seeing. All right, so one of the things that dust and gas, one thing that it does is it reddens the light, and the reason that it reddens the light is what's called scattering. If you ever, of course, you've seen a sunrise or a sunset, and you notice the light close to the horizon, as the sun gets closer to the horizon, either for a sunrise or a sunset, the light, it tends to be more orange or red, right before sunset or right before sunrise. You see this orange, and so what's going on there is what's called scattering. The red light is bouncing around off of dust particles that are larger close to the surface of the Earth, right? Just due to gravity, right? Right above our heads,